Yeah, as Alex said, I'm Rebecca Vickery. I'm a data scientist at Holiday Extras. It's a real honour actually to be the first speaker here, a female speaker. That's really lovely. So my talk today is about machine learning. What I'm going to talk about though is the part of machine learning known as data preparation. And in most machine learning workflows, that can be one of the most time-consuming parts. So one of the main reasons why data preparation is so time-consuming is because of the way that machines learn. So I'm also going to be talking about that today. So before I start, how many people in the room have worked with machine learning or have worked with machine learning in the past? Okay, a few, that's great. So a few people will have a good understanding of this already, but just for anybody that doesn't, I'm just going to recap on what machine learning actually is. And for the purposes of this talk, I'm going to be talking about supervised machine learning just to keep it simple. So with supervised machine learning, we have some data and we have some labelled data which are inputs. And we feed those to an algorithm, and the algorithm learns the mapping between the inputs and the outputs. And the goal of machine learning is that the algorithm can learn the mapping well enough to, with a reasonable degree of accuracy, correctly predict the outputs on unlabelled data. And how this works is with maths. Effectively, in the algorithm, it's performing very vast number of mathematical computations. And the maths is kind of from fields like linear algebra and calculus. But I'm not going to go into the maths behind it too much in the talk today. But it's just quite important for the rest of the talk just to kind of lay that foundation. So this is kind of what simple machine learning workflow looks like. So first of all, we need to get some data. We then train a model, so we train one of those algorithms that we talked about. Then we go through a process of model selection, so we want to find what is the best algorithm to use for our data. Then we tune that algorithm that we've found, and then we use the algorithm to predict on new data. And in the rest of the talk, I'm going to be going through some code examples, and just so you know, I work mainly in Python, so they're going to be Python-based. And I'm going to be using some of the open source data science tools like scikit-learn and pandas. So just to have a closer look at that workflow. So this is the get data part. So in this code, I am using a data set from scikit-learn's API called load wine. So this is a toy data set, so it's not really a real world data set. So in here you've got some features or the inputs that we talked about. So those are some features about different types of wine, and you'll see that the data is all numerical. And then at the end, hopefully you can just about see that, is what's called the target, and the target is what we want to predict. That's the type of wine that it is. So then what we next do is you want to fit a kind of a baseline model. So we want to fit kind of a stupid model, really, something. And to get an idea of the score that we get from that kind of stupid models, that we know when we're building our other models, our real models, that we're improving on that and we're not actually, in fact, doing anything stupid. And so a perfect score, so this, for simplicity, this is just something called the accuracy score. Perfect score is 1, so obviously anything closer to 1 is good. And so the next step, which I've talked about, is model selection. So in our problem here, this is known as classification because we're trying to classify some data into some categories. And for classification, just like any other task, there are a number of different algorithms that we could use for that. And we want to find out which one is best for our data set. And so what we do is we go through a process of kind of iterating on that to find the best one. And so what this code does here is takes a selection of those different algorithms, loops through them, outputs the score, and then what we can see is that the best score for our data is the random forest model. So that's the model that we would choose in this example. And then we want to go through a process of actually tuning that model. So all of our algorithms have different parameters that you can change, which will change the way that the model kind of learns. And so we need to find what the best set of those parameters for our model. And so one way to do that is with high parameter optimization. And we're using a tool called grid search, which is from scikit-learn. And what we're doing is just creating a grid of numbers around those parameters, so options for those parameters. And then again, we're using the grid search function to go through all those parameters, fit and train those models on all those different potential combinations. And what we can then access from that is a few things. We can access the best model. We can access what the best score was, and we can see that the score is perfect in this example. And we can access what the parameters were that gave us that best score. So now we know what our best model is. But in the real world, it's never that easy. There are far more steps in the process, and the accuracy score of 100%, I'm yet to ever see that on real data. So actually, it's never that simple. And actually, one of the most time-consuming parts, as I've already said, is data preparation. And the reason why it's time-consuming is because of this. So what happens when we have this data set? So the data set we had in our toy example was all numerical, and obviously because the algorithms perform mathematical computations, it works fine. But what happens when we have this data set? So this data set is from a website called Kaggle. Does anyone know Kaggle? Has anyone heard of that before yet? A few people. Good. So Kaggle is a machine learning competition website. So on the website, there's lots of data sets. Each one of those generally has a competition around it, so it's a problem to solve. You can take the data set, build a model, upload your results back to the website, and then hopefully place on the leaderboard. So this data set is from there. The data set is basically called the animal shelter outcomes data set. So what it is a series of animals in an animal shelter, some features about those animals, and then the outcome is whether or not the animal had a positive outcome or not so positive outcome. And so you'll see, as I say, that this is all string data or categorical data, so it's not numbers. So what happens when we feed that to our algorithm is that we get an error that says we can't convert this data to a number effectively. So what we need to do is perform some transformations to get that data into the right state. And that's why you often see this being said about the data science role, that most of the data scientist's time is spent on things like data preparation rather than on actually fitting and building those models. And it's true. And so one of the reasons why this is true is because machines obviously only learn from the data that they're given. They don't have any context beyond that. So if we're not very, very careful with how we transform our data or the data that we're giving our model, we can get outcomes that we don't expect. An example of this is from a few years ago. There was a group of researchers that published a paper in one of the leading scientific journals, I think it was Nature. What they'd done is they got some images of cancerous and non-cancerous lesions, and they would use an algorithm to predict whether or not those were cancerous or not. And it had really good results. But when people dug into that a bit deeper, what they found was that a lot of the images that were cancerous had a ruler in them. And that's because the doctors, obviously, when they find a suspicious lesion, the first thing they would do is get out a ruler to measure it, because obviously that's quite a predictor of that lesion being cancerous. And so what they found was actually the algorithm was using this kind of data point, this presence of this or absence of ruler, to predict. And so actually, the algorithm was performing well because of the data, but it wasn't particularly useful. So an actual machine learning workflow looks a bit like this. It can sometimes have more steps in it, but it's a bit more complicated than that initial workflow that I showed you. And the other thing is this suggests it's a linear process, but actually it's not. It's very iterative, this process. So generally speaking, you might go to model building and then go back to data preparation again or feature engineering to build a better model. So how do we turn that data set that we have with those categorical sort of string data values into something we can use to build a model? So we need to convert it into numbers. One really simple way we could do that is with something called label encoding. So with label encoding, we're effectively mapping the value to a number. So we're just saying neutered male is 1, spayed female is 2, intact male is 3, and so on. And that's a really simple way of doing it. The problem with that is that because of the way machines think and because of the way that machines have kind of a knowledge of the data, all we know that mapping. So we know that those numbers mean something, but all the machine sees are numbers. And the machine will look for relationships along rows, but also between rows. And so what the machine might do is think, well, this number is bigger than this number, and so this must be more important than the other number. And so what you might find is you get things happening that you don't expect. So a better solution for that is called one-hot encoding. So with one-hot encoding, it's a similar sort of thing, but what we're doing is we're taking each value, we're giving it its own column, and then within that column we have a 1 or a 0, whether it's present or not present. But that doesn't work for all of those data points that we have. So for example, we have ordinal data. So with ordinal data, that does have an order. So an example of that in our data set is the age. So the age is meaningful if we have a higher age or a lower age. And so with that, a good way of representing that is to turn it into its numerical version of that value. And what we've done here is just turn that into a day representation of that age as a number. But the other variables it won't work for are variables called high cardinality variables. So these have a lot of values in them. So for example, the colour in our data set has 366 different values in it. So if we were to use one-hot encoding, we would get 366 new features or new columns in our data. And what that does is it introduces a lot of noise, and it could lead to problems like overfitting, which is where the model fits really well to the training data set, but when you try to use it on new data, it doesn't perform so well. So how do we solve that? So one way we can solve that is with feature engineering. So with feature engineering, we identify some what we think intuitively are good features that might help the model to learn. And so one feature we might produce from colour would be single-coloured animals versus multicoloured animals. But the problem with that is that we lose a lot of information. So for example, I don't know whether anyone's heard of this before from a few years ago, that black cats aren't being rescued from shelters as often as other colours because they don't photograph as well. So if we didn't know that, piece of information, we might not code that, we might not engineer a feature around that, and we would lose that data. So there are solutions for that. So one solution is called weight of evidence. So what we're doing here is we are kind of producing the relationship between the variable and the predictor, or the class that we're trying to predict. And so, for example, in this, what it does is, say for tan, if we take tan as an example, it effectively produces a number that describes the distribution of tan in the positive class over the distribution of tan in the negative class, and it produces a number which shows that relationship. And so you can see here that we have that mapping, so it's either a positive or negative number. It's a positive number if it has a positive relationship to the positive outcome, and it's negative if it doesn't. And you can see here in this that the black here, that is the black cat, and it's got negative value, so it's captured that relationship. And weight of evidence is just one of many different solutions for this, and there are actually a whole load of solutions that do a very similar thing, that kind of map that relationship. But the problem is, in data science and in machine learning, as I said before, it's a very iterative process, it's very experimental. We wouldn't just take weight of evidence and just use that to encode our features and finish. We would want to test a number of different solutions. And so there are some solutions for that too. So one solution, I talked a bit about scikit-learn already. Scikit-learn has something called pipelines. So as I've said in the machine learning workflow, we have a number of different steps. And in our example, we've got some transformation steps where we're changing data, and then we've got some steps where we're actually training the model. And what pipelines allow us to do is kind of chain those steps together and apply them to different features. So we can say that we want the weight of evidence transformer to be on certain types of features, and we want the one-hot encoder to be on others. And then when we actually fit that model near the bottom of this slide, all of that is happening all at the same time as fitting that model, so we don't have to keep writing out all of that code. And then the other solution is a Python library called category encoders. Has anyone heard of this library? Nope. I think it's fairly new actually. What this does is it does all of that code for all of these different solutions. So even just weight of evidence, to hard code that, it takes a lot of code, it takes a lot of thought. And so what this does is it's already done all of that, and you can actually just call those transformers from just these little pieces of code. And the great thing about the category encoders library is it can be used in the scikit-learn pipelines. So what we can do here is we can call all of our different encoders, all the different transformations, put those into a scikit-learn pipeline, and then write some code that kind of loops through those, and again outputs the performance of the models using all those different encoders. And so we can find what's the best encoder or the best combination of those encoders for our particular data set. And so with all those solutions, we can reduce the time that data preparation takes. But there's still quite a lot of work to do, because as I've mentioned, I've touched on feature engineering a little bit in the talk, but I haven't mentioned it a lot. But feature engineering is actually really important on top of all these other transformations I've talked about. And actually it's still an important step. And Anthony Goldblum, the CEO and founder of Kaggle, he's very famous for saying this, which is there are only two types of machine learning approaches that win competitions, handcrafted or neural networks. By handcrafted, he's talking about feature engineering. So he's talking about handcrafted feature engineering. And feature engineering requires a lot of creativity, a lot of domain knowledge, things like that. So there's still a lot of work to do. But that's everything for me. Thank you so much for listening. If you're interested in machine learning, I do write a lot on Medium about machine learning. So you can follow me there, or if you want to follow me on Twitter, you can find me there. Thank you very much.
Thank you. Okay, so Q&A. Anyone got any questions? This is fun. No, nobody's got any questions? Hey. Yeah, we're professional.
So I've heard a lot about different types of machine learning algorithms. How does a random forest actually work?
Okay, so it's really hard to explain just standing here because it's quite complicated. But it's kind of a little bit like, it's effectively a decision tree. So it's a little bit like makes lots of decisions. So as I say with machine learning, the advantage of machine learning is that it does things on just a large scale. So if we had if we were doing a decision like we said, if we took a cat and we said, is it black or is it white? And then it splits those and then it will do the same thing. So it does that, it makes decisions basically at different levels of. Do you see what it means? It's kind of always made at different levels. It's quite complicated just to explain now. But effectively, that's great. Yeah. It's effectively it's a decision tree. So it makes decisions at different stages about things. So it's kind of on a large scale.
Thank you.
Okay.
Anyone else?
Yeah, I've got a question. When you're doing your...
Oh, okay, sorry. Hello, that's better, isn't it? Can you hear me?
Yes, I can.
Okay.
Yeah.
So you were doing your data prep in the actual, in the sort of Jupyter notebook, right?
Yeah, right.
Would you prefer to do it there, or would you do it outside through some sort of ETL process beforehand, or how would you do the two?
Yeah, so that's a really good point, actually. So obviously in my examples here, I'm using data sets that are CSV files from the internet. But in real life, I will be using a SQL query to get that data. And yes, I would do a certain amount of data transformation in the SQL. I would say there's a lot of advantages to using Python. So for example, one-hot encoding would be a bit of a nightmare to write into SQL. And similarly, the things like the weight of evidence I've talked about. So I think the data prep would be a little bit different than I would do in SQL, but absolutely, you're right. That's a really good question because a lot of that does happen in the SQL in the real world. That's right.